So shall we continue the discussion on chapter 2? So these are the list of the topics I want to discuss today. Basically, I want to continue the Gauss law. The Gauss law we discussed, technically it comes from the divergence of the electric field. And I'm going to do a few examples. And these examples are concerned with the special situation that we have very, very nice symmetry in the system. And that allows us to use the integral form of the Gauss law. Okay. So we're going to complete these couple of examples, 2 or 3 examples. And then I'm going to look at the curl of the electric field. And that is very interesting and also very important in the sense that the very special characteristic of the electric field is that the curl of the field is 0. And that puts the electric field in very special set of functions, a special set of vector functions where we can always define a scalar field and write the electric field in terms of the gradient of that scalar field, okay? And that's whole story about the electric potential, okay? So the curl of E actually is the reason that we can define electric potential. I'm going to define electric potential, and I'm going to discuss a few things about electric potential. If time permits, then I'm going to move on and connect the electric potential through a differential equation to charge distributions, and that's technically the Poisson's equation. And in the area that there's no electric field, there's no electric charge, that's going to be the Laplace's equation. Okay, so this is the things we're going to discuss today. And just a reminder from last Thursday, the Gauss law for electric field can be written in 2 forms. Okay, so one way which directly comes from the divergence of electric field is divergence of electric field is 1 over epsilon 0 times volume charge density. Okay, so this is technically the differential form of the Gauss law. Okay, the integral form you might be even more familiar with is if we do the integral of E dot dA, means integrating electric field on a closed surface, that integral should be equal to 1 over epsilon 0 times Q enclosed. And Q enclosed here refers to the total amount of charges within that surface, okay? That means if you have any random volume, you can look at the surface. If you have this volume, the surface is going to be closed surface. If you integrate E dot dA, that should be 1 over epsilon 0 times Q enclosed. Okay, so you can have many point charges or any sort of charge distribution within that volume, and Q enclosed refers to that. Okay. One thing interesting about it is that you can have electric charges outside. Okay, and those charges are not going to affect the integral of EDA. Okay, this is basically the flux of the electric field passing through the surface. Okay, so this equation is useful. Okay, it's always correct, but not always useful. This is very useful when we have certain case of symmetry. Okay, and if we have symmetry, we can carry out this integral relatively easy. Okay, if we don't have symmetry, it's still correct, but doing this integral is difficult, okay? And because of that, we don't really use that. Someone asked a question last Tuesday, if you use this in your research, a lot of times you will be a lot more comfortable using the integral, using the differential form, because that way you can solve the equation numerically and you will have some certain boundary conditions that you can use to calculate E numerically as a function of the charge distribution. Okay, so I'm going to do one example where we have very nice symmetry, and we're going to calculate electric field as a function of distance from a sphere which is solid sphere with constant uniform electric charge distribution, electric charge density. Okay, so the question is this. This is, by the way, this is one of the examples from the textbook. Imagine you have a sphere like this, okay, radius r, okay, so this is the sphere. And then you want to calculate electric field when you are at a distance r from the center of the sphere. Okay, so you could be outside or you could be inside as well. And the question is, what is the electric field? For these type of examples, it's easy to use the integral form. And the reason is that you have certain idea about the direction of the electric field only from the symmetry of the problem. Okay, so here, because of the spherical symmetry, we know what the direction of the electric should be. Okay, so can you guys guess, can you guys help me what the direction should be? So imagine you are here. What direction do you expect for the electric field? If you are in spherical coordinates, is it in radial direction or angle theta or phi?
Radial direction. Radial direction.
I can't hear you.
Yes, radial.
It should be radial, right? So you cannot have any field in any direction like this or this, okay? Because everything is symmetric. So if you have something, it should be either going out or coming in. Okay, so if it's positive, it's gonna point out away from the sphere, something like this, okay? And if it's negative charge, it's gonna be towards center. In any case, in radial direction, okay? So what will be the integral of E dot dA? We are integrating over a big surface, okay? So technically we should choose one Gaussian surface. Okay, so I'm gonna choose something so that I can draw, okay? So this is basically a Gaussian surface. If we are looking at the electric field outside this sphere, okay? So we do integral on this surface, okay? And the integral of the electric field dot dA, okay, runs over the whole surface of this. And because of the symmetry, we know it's perpendicular to the surface. And because of the symmetry, we know it's going to be uniform around over the surface as well. Okay, so here, this integral is 4 pi r squared. This r is a small r, and this is radius of the Gaussian surface. And this is technically the distance we have from the center of the sphere. And that's technically where we are calculating electric field at. Okay, so 4 pi r squared times E is this integral. Sounds good? Okay. Now, this has to be equal to 1 over epsilon 0 times Qm enclosed. So 1 over epsilon 0 Q enclosed. It's, if it has uniform electric charge, it's going to be 1 over epsilon 0. The volume of the sphere is 4 by 3 pi R3. Okay. And the charge density is rho, okay? Or I can just simply say it is 1 over epsilon 0 times Q, which is a total charge on this sphere, okay? So far, so good? Relatively easy? Okay. And now if you equate this side to this side, we have 4 pi r squared E, that should be equal to 1 over epsilon 0 Q, and that means the electric field, I'm just continuing on the top, it should be 1 over 4 pi epsilon 0 Q over r squared. And that is the magnitude of the electric field. because we know that is in radial direction, always, I would say that if I use vector notation, the vector E should be equal to this times R hat. Okay. Now, if you look at this, this is very, very similar to the electric field of the point charge. Okay. So what does it mean? We said we have a sphere with continuous uniform volume charge density, but if we are away from the sphere, we calculated electric field being exactly like the same electric field that we get from a point charge. Okay, and that is actually true. If you are away from sphere, you get electric field exactly the same as what you would get from a point charge. In a way, if you are away from this, you don't even care if it's big or small or how small it is, okay? As long as it creates electric field, the field is very similar to the point charge. So this is correct for electric field if we are outside this sphere. So I'm gonna write outside, okay? And outside here means R, the radius at which we are looking at the electric field is bigger than the radius of the sphere that contains electric charge, okay? So far, so good? Have you guys done this before? Maybe in 226? Okay. So now we're gonna look at the electric field inside the sphere, okay? Do you think there will be a big difference? What is the main difference?
Wouldn't there be no electric field on the inside?
Let's look at that. Maybe yes, maybe no. But I guess there will be because we have uniform charge distribution all the way to the center of the sphere.
Oh, gotcha.
If it was empty sphere and all the charge was distributed on the surface of the sphere, then yes, because if you go inside, there is no electric charge within that volume. But now I'm gonna draw another Gaussian surface with green. The Gaussian surface we choose should be something like this. And this is within the sphere, okay? The difference here is this. The integral of E dot dA is very similar to what we had before. It's gonna be simply electric field 4 pi r squared, with only difference that the r, the small r, is now smaller than capital R. That means we are within inside, okay? The difference is that the Q enclosed is not the total charge on the sphere anymore. Because you are inside the sphere, the enclosed charge is only the charge confined, encapsulated within this green, which is part of the whole sphere, okay? So I'm gonna write green here, the integral of E dot dA is 4 pi r squared times electric field, okay? Same as before, but then 1 over epsilon Q enclosed. Now, we should look at only the part that is within the sphere, and that is integral of, you know what, we don't need to do the integral. We have the radius, we have the charge density, right? And that is 1 over epsilon. The whole volume is 4 by 3, sorry. The total volume of the green sphere is 4 by 3 pi r cubed, and that should be multiplied by charge density. Sounds good? And then if we equate these two sides, the right-hand side of the equation, we have 4 pi r squared E equal to 1 over epsilon 4 pi divided by 3 r cubed rho. 4 pi cancels out, r squared cancels this, and electric field is, so I'm gonna write with black, electric field is 1/3 epsilon 0 times charge density rho times r. Okay, so this is what we get when we are inside. Okay, so if you look at this, if you are outside, the electric field drops as a function of distance. The farther you go from the sphere, the smaller electric field you get, and that declines as a function of 1/r². If you are inside, the electric field increases as you go away from the center, and that is because as you go away from the center, you are actually covering more and more electric charge within this Gaussian surface, okay? So more electric charge is used to create that field. It's useful to draw a diagram of the electric field, okay, where we can look at the strength of electric field as a function of distance from the center of the sphere. By the way, I'm going to change this to vector notation and add r hat here as well. Okay. So I think here is good. Okay, so I'm going to draw a diagram and look at the strength of the electric field E as a function of radius. And let's imagine here is capital R is the radius of the sphere that we have. So here is technically inside, and here we are outside. Okay, so if you are inside, we should follow this. If you are outside, we should follow this. Okay, so outside electric field drops proportional to 1/r². And if we are inside, the electric field increases linearly as a function of r. It's pretty much like this. This is proportional to r. Looks good? Okay, so the main reason we could follow the integral form of the Gauss law here is because we have a specific symmetry here, and that allows us to come up with some certain assumption about the direction of the electric field as well as the uniformity of the electric field. And the integrals of E dot dA becomes easy integrals, okay? Otherwise, it's going to be very difficult. Not that it's not correct, it is correct, okay? But conducting the integral of E dot dA could be difficult if we did not have this symmetry. Okay, any question?
What example is this in the book?
What example is this? The example of the book only calculates outside. I added inside myself and this curve myself. Okay, no, I can bring the book and see which example that is. I think there's a section under name of application of the Gauss law, and that is
Professor, what's the equation on the right side of the graph?
the equation on the right side of the graph. This is proportional to 1/r².
Oh, gotcha.
Alpha is proportional.
Gotcha.
Okay, and this one is proportional to r. So this is extended version of example 2.3 on page 71. Yeah. All right. Anyone taking notes? Shall I erase this? Yes means yes, I can erase, or no?
Yeah, you can erase.
Oh, okay. So I'm gonna erase this part. All right, so I'm gonna do a couple of more examples. Okay, and hopefully we can do it together. So I want to get some input from you guys as well. Very similar case, if we have cylindrical symmetry, a seal, through the symmetry, we can make assumption what are the directions of the electric field and so on. Okay, so the question here is, I guess example 2.4, yes. Example 2.4, the question is we have a very long cylinder, extends to infinity, okay, and that has electric charge distributed over the volume of the cylinder with the equation of the charge density is proportional to a constant times S. S is the distance from the axis of the cylinder, okay? So if you're sitting at a distance S from the center, okay, the volume charge density is rho times K times S, okay? So the question asks, what is the electric field outside? We can also calculate electric field inside the cylinder. Okay, so E, here is the question. Okay, so again, this is a case that we have symmetry, and through the cylindrical symmetry, we can guess electric field only has radial component. Okay, it does not have any component in the Z direction. Okay, it only has component in the S direction. Okay, so how do you choose the Gaussian surface in this case? And how do you calculate this integral? And what is the enclosed electric charge within that surface? Okay, so for questions like this, always the very first step is choosing the right Gaussian surface. That makes doing the integral easy for you. Okay, so I'm asking you, how should I choose this? If I want to look at the electric field right at this point.
Would we want to look at it like as if we're like looking into the tube?
Yes, but for the surface, for the Gaussian surface, we should choose a volume, right?
So like a volume going around the tube?
It should be a volume. Technically, it should be a cylinder because we have cylindrical symmetry. We should just follow that, okay? And that has to be right at this point, and then it covers the whole area around the cylinder. Okay, so if you're at distance S from the center, the diameter, the radius of the cylinder should be S all the way. Okay, so if we choose like this, the advantage is that the electric field at any point on the surface of the cylinder is uniform. Okay, so it doesn't matter if you're looking at here or here, the electric field, the strength is uniform. And the electric field on the surface of the circles, on the sides of the cylinder, is non-zero. Okay, it has certain value and it's dependent on the distance from the center, but the point is that it's parallel to the surface. Okay, so integral of E dot dA on the sides of the cylinder, it just vanishes. It's zero. Okay, electric field is not zero, but electric field is parallel to the surface. That means the dot product of E dot dA becomes zero, right? On the surface, electric field is always perpendicular to the surface. So the dot product is just, you're multiplying by the cosine of 90 degrees, the cosine of 0, which is 1. Okay, so if we do E dot dA on the surface of the green cylinder here, what we get, okay, what we get from the surface here is 2 pi s times, we need to choose a parameter for the length of this cylinder, 2 pi sl times E, okay? And this solely comes from the curved surface of the cylinder. From the sides, there's no contribution, so we just forget about that part. Is it clear for everyone why it's 0 on the surfaces, on the sides of the cylinder? Okay, it's just because of the direction of the electric field. Otherwise, the value is not 0. Okay, so this is what we get for the integral of E dot dA. What is the enclosed charge within this green cylinder? So it's technically a portion of the very long cylinder we have, right? The portion that is within this part. Okay, with the length of L, diameter of the cylinder, let's assume it's R. Okay, we have the charge density as K times S. So what we should do, we should integrate the whole charge density over this specific volume of the cylinder and see how much electric charge we have. Okay, so Q enclosed, technically it's an integral over the volume. Okay, so charge density times d tau. This is infinitesimal volume, and rho is charge density. And this is basically a triple integral because it's three-dimensional. So it's going to be triple integral. K dot S is a charge density. Okay, and the tau for cylindrical coordinate is ds times SD phi times dz. Okay, here the z-axis is this side, and S is radial direction, and phi is around the azimuthal angle. Okay, so it's going to be Ks times ds d phi dz. We have one more S from the azimuthal angle, infinitesimal displacement, and that makes it Ks2. Okay, so this integral, triple integral, runs over z, phi, and s. What are the limits for each of them? For the z, we are moving from this point to this point. Overall, it's going to be from some point to that amount plus L. Okay, so I can say that this is from, let's say, Z naught to Z naught plus L. Okay, that's the limit for Z. For phi, it always goes from 0 to 2 pi. So it goes from, it's getting a little messy here. Let me rewrite this integral. Okay, so it's one integral of z from z naught to z naught plus L. Integral of phi goes from 0 to 2 pi. And the integral over S goes from 0 to R, which is the radius of the cylinder. Sounds good? Okay. So these integrals are in fact pretty easy. The first integral for z, there's no z component except dz here, so that only gives us a factor of L because that's the distance it's covering. Okay, so I get L out of the last integral. The integral of phi, we only have d phi, there's no phi dependence here, so I only get a factor of 2 pi. So 2 pi L is basically from the two integrals. And then we have integral of S from 0 to R. 2 pi L K S square ds. Okay, and now everything here is constant except S to the power of 2, and that makes the whole integral 2 pi L K divided by 3 times S to the power of 3, and with the limits of R and 0, we get R to the power of 3. Looks good? So this is the total charge we have within that sphere. Okay, so looking at this and this, combined, we can write electric field in terms of S and the confined electric charge, okay? So 2 pi SL E, 2 pi SL E should be equal to 1 over epsilon naught times the enclosed charge. And that means 2 pi LK by 3 epsilon naught times R3. Okay, so a lot of these things can be canceled out. The most importantly, L, the length of the Gaussian cylinder, cancels out. Okay, and I think it's easy to imagine the electric field should not depend on the length of the Gaussian cylinder that we chose here. Okay, that's a hypothetical cylinder. Okay, so whatever length we choose, at the end somehow it should be canceled out so that E becomes independent of L. Okay, and that is nicely canceled out here. We got 2 pi here that cancels this. We have S here. Okay, that is only non-constant that defines the decay of the electric field. So E is K R cubed 3 epsilon 0 over times 1s. Okay, that means that as we go farther from the cylinder, the electric field decays as a function of 1 over s. Okay, so the strength of electric field, if I plot it as a function of s, it drops proportional to 1 over s. Okay, and this is electric field outside the cylinder. If we are inside the cylinder, still we can use the same similar approach to calculate the electric field. The only difference is that the integral here is not from 0 to capital R, it's from 0 to a small s, which is the distance we have from the surface. Okay, so here we're going to get s to the power of 3, and here, instead of R, which is a constant, we get s to the power of 3. So we're going to get electric field that's going to increase as a function of s squared. Okay, so I'm not going to do the details here. Okay, I let you do it at home. It's a good practice for you. But simply it becomes s to the power of 3, cancels out with this s. We get eventually s to the power of 2. We get increasing function, parabolic function. So this is proportional to s to the power of 2. That's how electric field increases. So if you're right at the center, there's no electric field. As you move from center to the surface, the strength increases. As you move from the surface all the way to infinity, it starts decreasing again. Okay, and that's what we expect, right? We expect if we go so far away from any charge distribution, we get 0 electric field. Okay. And that's most of the time correct, except that in hypothetical cases where we have electric charge distributions extending to infinity. Okay, so the next example, relatively easy example, we have plane symmetry, and that's the sort of electric field that we get. It's not going to vanish at the infinity because the charge distribution extends to infinity as well. Okay, so any questions so far?
I do, only with the limits of C. I understand why it says equal to C naught. I'm struggling to see why it's C naught plus L.
Which part?
On the triple
Z
integral?
naught plus L, because covering from one point here all the way to here, right? So if this is Z naught, it's going to be Z naught plus L. That's how much we're covering on the Z axis.
Okay, thanks.
Sounds good?
Yeah.
Any more question? Cool. Okay, so if there's no question, I'm going to move on to another example that we have infinitely charged plane. I mean, infinite plane carrying charge density. And we're going to look at what kind of electric field that creates. Okay. So this is another case. We have symmetry. We can use the integral form of the Gauss law. Okay. So imagine we have this plane. And imagine it extends all the way to infinity and it carries a surface charge density sigma. Okay. The question is what kind of electric field we get above and on the other side of the surface. Okay. So if we want to look at only the cross section, you can imagine we have a plane like this. The surface charge density sigma, the question is what is the electric field here? Okay. The surface is super, super big, extends to infinity. The first question I want to ask you is this. How do you think the electric field should depend on the distance, let's say S, from the surface? Do you expect it decaying as you go further? Being constant?
No, it should
Of course,
decay.
it never increases, right?
It should decay as you go farther away from the plane.
Yeah. In a case that this is not infinitely large plane, as you go further from this, you are going away from the charge distribution and you're going to see that distance. The further you are, the smaller charge distribution you're going to see from distance, and you expect that electric field is decaying. Okay. But in a hypothetical case that the surface extends all the way to infinity, what happens is that no matter how far you go from the surface, in your perspective, you have the same large infinite plane. Okay. You go further away, you have the same sort of charge distribution. Okay, so interestingly, as a result of that, because it's infinitely large plane, you don't see any decaying field. Eventually, you're going to see a constant electric field. Okay, so this is just intuitive explanation. I'm going to use Gauss law to show that no matter how far you are from the charged surface, the electric field remains constant. Okay, so let's look at the Gauss law and first choose a Gaussian surface, and then let's look at the electric field that we get from this. Okay, so my question for you, how should I choose a Gaussian surface here? Something symmetric, right? And that should probably cover both sides of the surface, and I would say that the best way is choosing something like this. Okay, so if this distance is S, let's choose something symmetric so that this one is S as well. So we are covering, this is technically a box that is covering both sides of the surface. Okay. So if I want to show it in 3 dimensions, something like this. Something like this, and this is the surface, and it extends to the other side as well, if it helps. Okay, and this is only the cross section. At distance S, and here is distance S, so the electric field on both sides are supposed to be almost the same. Sounds good? So what should be the integral of E dot dA here? how do you think about the direction of electric field right at this point on the sides?
Is this a surface that we're doing it for?
So this is the surface.
Okay, so it's like a plane.
It's like a plane.
Okay.
This is just a cross section. And this is above, this is the bottom.
Gotcha.
Okay, and of course, if it's surface, it has plane symmetry, above and bottom, right?
So they would cancel out?
So we have electric field here pointing up, we have electric field here pointing down. Okay, and another thing we have is on the surface, on the sides, okay? So we do have electric field here as well, probably pointing up here if it's positive surface and down here. But the point is that the direction of the electric field, very similar to cylindrical case on the sides, this is pointing exactly in the same direction of the surface, okay? So when it comes to the integral of E dot dA, the side surfaces do not contribute at all, okay? And that's only because the surface is parallel to the electric field, okay? But the top surface and the bottom surface contribute to this integral, okay? If the electric field is E here, okay, because of the symmetry, we can say this electric field is uniform on the surface. And because of the same reason, we can say this is uniform on the surface. Now, if we have this E dot dA, these two surfaces, and let's imagine the area of each of them is A. Okay, area of each of them is A, so E times A is going to be contribution from the top surface, right? The same, E dot A is going to become contribution from the bottom surface, okay? And the side surfaces, they are zero. Technically, there are 4 side surfaces, all of them are 0. So this is basically the whole integral of E dot dA. Sounds good? So this is the all contributions we have on this box, integral of E dot dA. Is it clear for everyone? Why is it uniform here? Why it's 0 from the side? The contribution from the sides are 0? Yes? Okay. So if not, please stop me, okay? And then what is the enclosed charge within this box or here? Can someone?
Just be A times the charge density.
So the enclosed charge is a charge within this box. Okay. So that amount of the charge on the surface, this part, is the enclosed charge. What is the surface charge density? Sigma. Okay, so the total enclosed charge is A times sigma. Sounds good? Easy? And now let's connect these two together. 2 times EA should be equal to 1 over epsilon naught Q enclosed, which is 1 over epsilon naught sigma. Okay. Now, sorry, the Q enclosed is A times sigma. Looks good? So now, the electric field is simply sigma over 2 epsilon 0. Very simple. And I say very simple because it turned out it's not dependent on S, the distance at all. Sigma is a constant, 2 is a constant, and epsilon naught is a constant as well. Okay, so this is mathematically the same concept I discussed. If we are away from an infinitely large plane, no matter how far we are, basically we don't see the distance because the surface extends to infinity. Okay, and no matter how far we go from this, the electric field is just zero. Sorry, electric field is just constant. Sounds good? Any question? No? Okay, so let's see, it's 10:26. We're going a little slow, but that's okay. So we covered the Gauss law here so far and the examples for this. And the next thing I want to discuss is the curl of electric field. Okay, so let me get rid of all this. Okay, so the curl of E, this is very special, as I said, because the curl of E turns out to be zero, and that gives us all the possibilities of defining electric potential as a scalar field whose gradient is equal to electric field. And that makes it a lot easier because of the variety of things. First of all, that is like summarizing electric field, which is a 3-component vector, into scalar field, which is a 1-component function. Okay. But now let's start from beginning and say why is the curl is zero and what are the benefits of that. To start that discussion, what I want to do is that I want to look at the point charge, and I want to look at the electric field around that point charge. Okay, and then I want to do one line integral starting from one random point in space A to a random point in space B, and I want to integrate over a random path. Okay, so imagine we have this point charge sitting here, and imagine this is point A in a space, and this is point B in a space, completely random, and I connect these together with this random path. Okay, so we go along this path, and I want to calculate the integral of electric field from this point charge, let's say Q dot dl all the way from A to B, and I want to go around this random path. Okay, so one easy way to do this, because the electric field from point charge has a spherical symmetry, I want to use a spherical coordinates. Okay, so imagine this is my coordinate system X, Y, and Z. I'm assuming that this point charge is sitting right at the center origin of the coordinate, and I want to look at the electric field and dl as well. The electric field, easy, that's 1 over 4 pi epsilon 0 Q divided by r square times r hat. Okay, and dl in a spherical coordinate is what? dl is dr times r hat, the radial component, plus r d theta, theta hat, the polar angle, plus r sine theta d phi phi hat, the azimuthal angle. Okay. So with these two, this and this, E dot dl is, if we do the dot product, the second and third term are not in the direction of r hat, so the dot product, the last two terms don't contribute. Only the first term is important, and from that we get 1 over 4 pi epsilon 0 q by r square times dr, and then r hat dot r hat is only 1. So this dot product, we get a scalar like this. Okay, so now if we integrate this from a to b, we are integrating, let's rewrite E dot dl, that's going to be equal to q over 4 pi epsilon 0 integral of dr r square a to b. Okay, so the integral of dr over r square is going to be negative of 1 over r. Okay, so we get negative of q 4 pi epsilon 0 1 over r from a to b. Okay, and here we get q over 4 pi epsilon 0 1 over RA minus 1 over RB. Sounds good? So there is something specific about this. We do this integral, and I said we are doing over a random path, okay? And we wrote dl in a very general form. Okay, we included theta hat and phi hat directions as well. But at the end, everybody canceled out. It turned out it's only dependent on radius, okay? And the way we integrated, eventually it's dependent on RA and RB. So it depends on the starting point, it depends on the end point, okay? But not depends on the direction and the path we chose, okay? So this is very specific type of integral. You do it over a line, at the end, the result is only dependent on the beginning point and end point, okay? And that's also in a very special way, it's only dependent on the radius as well, okay? So now, you can easily imagine if I had done this integral, okay, E dot dl, over any closed path, right, the result would have been 0. Because if it's over closed path, you start from one point, again, random closed path, okay? You start from one point, you can go all the way around any random path, but come back to the same starting point. If you come back to the same starting point, that means RA and RB are equal to each other. So the parentheses here just becomes 0, the integral becomes 0. So for this integral E dot dl, we have this specific situation that over a closed path, the integral is 0. And I guess that's relatively obvious from the mathematics we did here, okay? Now, if we go back to the stuff that we discussed in chapter 1, and if we look at the Stokes theorem, the Stokes theorem says that any integral on a closed path, okay, any vector function on a closed path, the amount of this integral should be equal to the integral of the curl of the function, which in this case, curl of E, over dA. And that, the first integral is all on the path, closed path. The second integral, okay, is on a surface. And that is a surface, any possible surface that connects that path, okay? So it could be straight, or it could be a curved surface, any surface that connects that path, that's loop, the curl of the function dot dA, these are equal to each other. Okay, so in this case, E dot dL is 0. That means the curl dot dA should be 0 as well. Okay, so we get this one. Okay, so the curl of E over any closed path, any surface is 0. If this whole surface is an arbitrary random surface that we can choose, and if it's correct all the time, that means the curl of E must be 0. Okay, so the curl of E at any point must be 0 in order to satisfy this integral all the time on any random surface. Sounds good? Okay, so if we have point charge distribution, curl of E is 0. Okay, any other charge distribution, I would argue that they are like a combination of different point charges. Okay, so if it's correct for point charge, it has to be correct for any other possible charges as well. Okay, so with these arguments, we would conclude that curl of E is always 0. Okay, and now the advantage of that is this. If, you know what, let me clean up the discussion on the point charge and then continue right from here. Okay, so let me get rid of this. So the curl of E is 0. Okay, and I don't know if you remember the product rules for the del operator that we discussed in chapter 1. We had certain second derivative of the del operator, and one of the products was like this: the curl of the gradient of V. Okay, so it was one of the second derivatives that we discussed, and we said if you expand it, you can write it in terms of the derivative with respect to each component, and if you use curl, you make a determinant. At the end, the derivatives were such that it becomes always 0. Okay, and the idea is that the curl of any gradient is 0. Okay, and this is closely related to the curl of the vector function being 0. Okay, so if the curl of a vector function is 0, we can always write that function as a gradient of another function. And in terms of the electric field, we write it in terms of negative of the scalar function. Okay, and that is actually the electric potential. Okay, so these are closely related to each other. As soon as the curl is 0, and we can assume that we are taking the curl of the gradient of the scalar function, and that means we can write this field, we can write this vector function in terms of the gradient of the scalar function. Okay, so what I want to do next is I want to define what the electric potential should be. Okay, again, I'm going to start from point charge, and then I want to expand on what are the specific properties of this electric potential. Okay, so we have like 6 minutes. I think I can start and give you the definition, and then comments and discussion we're going to continue on Thursday. Okay, so let's get rid of this. I'm going to keep this at the top because that's important. Okay. So if the curl of is 0, we have a few more properties always as well. Okay. One is if you integrate E dot dl, as we already saw from 2 points A to B, the integral is independent of the path. Okay, this integral is another property is, again, if you do the integral on a closed loop, that is always 0. Okay, so V dot R, I want to define it as an integral of E dot dl from a random origin, okay, all the way to the point R. Okay, and it's important for you to note that this potential, let's say, is calculated at point R. This point is technically the limit of the integral here, and nothing inside is dependent of R. Okay, so this R is the limit of the integral here. The origin here, we're gonna discuss that further. This could be technically any point of interest, okay? It could be any point that you want, and you can always measure the potential, electric potential, with respect to this point, okay? For a lot of cases, infinity is a good choice, because if you go at infinity, the electric charge is 0, and you can assume that electric potential at that point is 0, okay? But at the end, it's up to you. You can choose any value. And later we're going to discuss that the value of the electric potential is not that of important. What is important is how much potential changes if you go from one point to another point, okay? So, but most of the time we use infinity as the origin for the potential. So if you're integrating something like this, you're integrating from infinity to this point, okay? So I'm going to define potential like that. And then the difference in potential, let's say from VB minus VA, okay, that is equal to negative R integral from the origin to B, A dot dl, plus the integral from origin to A, E dot dl, and that is equal to integral from negative A to B, E dot dl. Okay, so based on this definition, if I look at the potential at point B minus potential at point A, it becomes two integrals, and these integrals overlap in a way that we can write it as one integral from A to B. Each of these ones are from origin to B, from origin to A. I can write it in terms of the A to B, okay? And if we do this, the fundamental theorem for gradient, which was the topic of quiz last week, okay? The fundamental theorem for gradient says that VB minus VA is integral of A to B gradient of V that dl. Okay, so this is mathematically true all the time. This is a fundamental theorem for gradient. But what I want to do now, I want to compare the left side of this, okay, with left side of this, and the right side of this with this, okay. So I started from this definition for potential. I could write this one, And now comparing these two, following the fundamental theorem for the gradient, I see that this integral of gradient of V dl is exactly equal to the integral of E dot dl. Okay, and from that I can conclude that starting with this definition of the potential, the E electric field can be written as a negative of the gradient of the electric potential. Okay, so this is basically the differential form of the definition of the electric potential, and this is the integral form of the definition of the electric potential. Okay, so the time's up. I want to stop here. On Thursday, I'm going to start from this and these two definitions, and I'm going to discuss several properties of the electric potential. Okay? And then I hope with these discussions, we will have a better and more clear conceptual understanding of what electric potential is. And after that, we're going to do a few examples of calculating electric potential and for specific cases and whatnot. Sounds good?
Sounds good.
Any question? Okay, so I'm going to stop the class right now. You guys enjoy the rest of your day, and I will see you on Thursday morning.
See you, Professor.
Okay.
Thank you.